Welcome to the course on principles of vibration control, and today we are going to talk about a very special type of vibration controller which is known as proof mass actuator. See that how this kind of proof mass actuators can be applied in terms of active dynamic vibration absorber. Now, the basic principle behind the proof mass actuator is very simple. Suppose you consider that there is a a body like a submarine hull or some such system or an aircraft platform which is subjected to. So, this is the body of it and this is subjected to some kind of an harmonic excitation, a wave is propagating through it. Now, in order to resist the response of this system, so under certain conditions it may go up or down like this, but in order to resist these kinds of vibrations of the hull, what it is generally done is that there is a magnetic proof mass system, which I will show you the details of it in a minute, which is attached to this system. It may be with or without a damper, but this is what is known as a proof mass actuator, and the role of the proof mass actuator is to apply once again a harmonic wave back to this system. Okay. So, when for example, this is going up, at that time you apply a force which is going down dynamically and back and forth like that, so that you can suppress the dynamic response of the system. So, that is why this is also sometimes known as sky hook damper. It is a very effective technology for particularly submarines and ships, because both for submarines and ships there is this problem that the power source of it, particularly for defense applications, the power source are very much susceptible to this kind of vibrations, and if depth charge or if an enemy shock wave created by an enemy kind of a bomb or something, if that creates a problem in these particular generating system, then the entire system will be down. So, as a result, people generally apply this kind of proof mass actuators on such defense equipment, so that this kind of vibration is not allowed into the system. Now, let us look into how such a system would be actually, what is it inside this proof mass actuator. So, if you look at it, that this is the proof mass, or so to say that mass part, inertia part of the proof mass actuator, and then it has basically permanent magnet. So, this is actually the permanent magnet part of it, and if you look at it, that this proof mass is sitting on electromagnetic coils. So, that is the electromagnetic coil system, and a kind of a spring and a damper. It is a kind of symbolic representation, but basically attached with the way it is attached with the permanent magnet may be considered through a spring and a damper. So, that is what is the total kind of the construction of proof mass actuator. Now, this particular coil that it has, you may consider that this coil has can be represented as something which has a resistance R and an inductance L. So, the coil can be represented in terms of a resistance R and an inductance L, and there is a voltage that we are actually applying to that system, okay, and through some kind of a source we are applying this voltage, okay, power source, and the current is passing through this whole thing. And what happens when I pass the current through this solenoid? This becomes a magnet, and you can design this magnet in such a manner that you can generate the poles in it, and these poles will essentially control the motion of this particular brute mass actuator system, because if there is a north creation, then there will be a repulsion, and the southern will be, south part will be actually pulling it. So, you can actually generate a kind of a motion in the brute mass actuator by controlling the current in this system. Now, if we actually try to find out the governing equation of this, we will find that one important thing that will come into the motor model is called the back EMF. Okay. In motor, actually you need two things. One is called the armature constant, which you will be knowing. It typically depends on these coils, the coil density, coil materials, etc. But the back EMF also is an important factor, and you might have noticed it many a times in your day to day experience. Suppose whenever a refrigerator or an air conditioner, anything which has a compressor and the motor, when it first starts, you see that the light often dims momentarily. Now, the reason is that because this motor has coils and inside the magnetic field, and the coil is turning inside the magnetic field, will actually induce a back EMF in that coil itself, which will act against the applied voltage, something that is producing the magnetic field. So, thus it will reduce the current flowing through the coils of the motor. You can do a simple calculation, like if the applied voltage is delta V, for example, and you know the coil resistance R, then you can find out that what is the current that will come up in the system, and for that delta V applied voltage of suppose 120 and a resistance of 6 ohm, you will get a 20 ampere of current. So, that means this much of current will be actually drawing from the system in order to actually counter this magnetic field, and since this current is getting drawn from the system, so the lights dim because that current is getting drawn back to the system. So, thus you can actually see this kind of manifestations of the back EMF. Now, in the motor we can actually find out that what is the EMF and what is the back EMF constant, depending on the various factors of the motor and the load requirement. So, if we look into the governing equation of the system, so what we have is that we have two systems with us. One is an electrical part. So, let us first discuss the electrical part. In the electrical part, as we have seen that we have a resistance R, and along with that in a series we have an inductance L, and we have a voltage source here from the motor. Okay. And there is a direction of the current which is flowing through it, right. So, that is, let us say it is I. So, that means the drop is here R I, that is the first part, plus the second part is actually L d I dt, and that equals to the applied voltage V minus of course the back EMF, and that is kb times the velocity of the brute mass actuator, because as it will be moving up and down, proportionately this back EMF will be generated. So, kb x dot, the faster it will be moving, the more will be the back EMF, and the slower the less, etc. So, that is what is my first equation. And the second equation, if you look at it, that is simply, once again you have to draw that free body diagram, because this is electrical equation, okay, from the electrical part of the system, and this is from the mechanical part of the system. So, together this becomes a electromechanical system. So, for that mechanical part of the system, we have the MP as the brute mass with us, and it is moving down, which means an inertia force of MP x double dot is working on it. Also, the spring resistance Kpx corresponding to the displacement here, and the damper if you have, that is Cpx dot, and all this thing is happening against a working force which is working on the system, and that is Ka, that is a armature constant, and that is proportional to the current that is passed into the system. So, if I pass more current, I get more Kai and I get this part running, but my Kb also, once it runs very fast, my Kb also will increase. So, this is the mechanical part. If I consider now this equilibrium, the mechanical part will be clear to you. What you can further do is that these are two ODEs, right. This is the first one is a first order and second one is a second order ODE. So, you can convert both of them in the frequency domain. So, then you get actually I as one of the frequency domain variable, capital I, capital V bar and capital X. So, I get these three frequency domain variables and I get a new set of equation. The first equation is Ri plus Lsi, which equals to V bar minus KBSX, that is after carrying out the Laplace transform. So, from this you can actually get a relationship, because you know that R plus SL times I equals to V bar minus SKBX. So, you can find out what is I, which is 1 over R plus Ls times V bar minus SKBX or KBSX. Similarly, from equation 2 also you will get, now in both the cases I have considered of course 0 initial condition. Now, in the second case what you are going to get is S square MPX, that is from the first term, then KPX from the second term, and then SCPX third term equals to KAI. So, here also I can take all of these things and I can take the x out. So, I get this particular equation, and combining this 3 and 4, because you already have this relationship of what is I, you can get a relationship between V bar, that is the applied voltage in frequency domain, and x. Now, let us see what is the relationship we will get. So, if you look at it, that if I combine the two equations, I am going to get this particular relationship, and a little bit advanced, if I put 1 over R plus Ls, now R plus Ls, this Ls R plus Ls can be written as the impedance. So, Zs is actually the impedance of the system, and A tilde is actually reciprocal of impedance. So, this is the reciprocal, and it is also known as admittance. So, if I denote 1 over R plus Ls as 1 by Zs and that equals to A tilde S, which is the admittance, then I get a bit of a simpler relationship where I can club all the x terms together. That means, I get S square MP plus Kp plus Cps plus SKA KB A tilde S. Okay, so, that is from this part of it. This whole thing times x equals to right hand side K A tilde S times V bar. In other words, my relationship between the output and the input is actually governed by this particular part, that is K A tilde S over in the denominator S square MP plus Kp plus SCP plus KAKB A tilde S. So, that is what is my representation, and hence I can write down also another thing. If you want to express this whole thing in terms of the force, then you can check that the force that is transmitted to the base is minus MP x double dot. How can we see that that is what is happening? Well, because if you consider that this is what is your MP and only consider the mechanical part of it. So, MPx. So, you can see that here, because it is in dynamic equilibrium. So, it has these two balancing forces, one is Kpx and another is Cpx dot. So, on the support also it is the same thing that is going to work into the system, that is the combination of kpx plus cpx dot just in the reverse direction. So, that means if you look at the earlier governing equation that we have, so if we just have a look at it, you will see that we have this relationship here where we have this mpx double dot plus kpx plus cpx dot equals to kai, and since we are considering this effect itself, so this will be equivalent to, as you can see in this case, that this kpx plus cpx dot, the total of them is equivalent to what is the called the mpx double dot part of the system. So, the force that has to be generated has to be the negative of it, because it is in the opposing direction. So, then Ft is minus mpx double dot. Now, if you use Laplace transformation, then it will become minus s square mpx, and now you can combine these two equations together, and if I do that, then I am going to get this relationship between Fs and V bar, and where we can see that we have in the numerator minus s square mp k 8 tilde s, and in the denominator we have s square mp plus kp plus s times cp plus k kb a tilde s. Now, we have to keep in our mind that the first of all the order of this transfer function is that this is a second order transfer function. When we will discuss about closed loop system, we will talk more about it, but actually the order of the polynomial of the denominator is telling us about what is the order of the transfer function, and because of the presence of this s square, we can say that yes, it is a second order transfer function. Secondly, the response of this second order transfer function can be actually controlled by controlling the MP, the proof mass itself, the Kp, that is the the spring stiffness, the Cp, the damping of the spring, the armature constant Ka, and the back EMF Kb. Generally K and Kb are same, and finally the impedance of the system, which is 1 over Zs. So, by varying all these parameters, one can actually vary the response of the second order transfer function. Now, we will see that okay, if this is the force F that is generated by the proof mass actuator with an application voltage V bar, can we put it back into a system where we need to control the vibration, similar to what I had discussed in the very beginning. Okay, so, we will be now talking about how we can apply this proof mass actuator in a system which is undamped or underdamped. Now, let us say we disregard the damping part of that system, and let us say that the mass of this system for whose vibration I want to control using proof mass actuator is m1, stiffness is k1, and it is subjected to a dynamic force which is coming, the source is the proof mass actuator. So, that is what we have to keep in our mind, because we have to plug in this proof mass actuator equation into the whole system. First thing is the equation of motion. Once again, that is pretty simple for us, because we have the mass m1 here, and this mass is of course subjected to what you call the base excitation. So, corresponding to its displacement x1 here, it is getting an inertia force which is m1 x1 double dot, and so m1 x1 double dot, and it is also having a spring force which is k1 and x1 minus y. Okay. So, because it is subjected to a base excitation, that base excitation is the vibration wave that I told you is coming because of the shock that the structure has been subjected to. Now, so these are the two forces, and now if suppose if I did not have the proof mass actuator, then it would have been m1 x1 double dot and plus k1 x1 minus y equals to 0. That would have been the case of a base excitation system, and you can see that since there is no damping present in the system. So, you would have seen with respect to in the frequency domain with respect to the transfer function, you might have seen that it is going to have an unbounded resonance of the system. But now, if we introduce this particular forcing function part, so that means I have an additional forcing function part which is coming due to this proof mass actuator, and that is Ft. So, then my equation is non-homogeneous and I am going to get this equation with us. Now, this equation, let us quickly convert it using in the frequency domain using Laplace transformation. So, I am going to get it as S square m1 x1, that is from the x1 double dot, and then plus k1 x1 minus k1 y equals to Fs. I can take all these x1 related terms in one side. So, it is S square m1 plus k1 x1 equals to Fs plus k1 y. In other words, x1 equals to Fs plus k1 y by S square m1 plus k1. So, this is what we are going to see in terms of a relationship between x1 and the y as the the base excitation input. But we have the Fs with us. Already we know the relationship of Fs, which we have earlier seen, that there is a second order transfer function between Fs and the applied voltage V bar. So, let us plug in this relationship here. So, let us put this part Fs into this relationship. So, what we are going to get now is x1 as a function of k1 y, that is the input, and the voltage that I am applying to the system. So, I have a mechanical excitation, this is the mechanical excitation part, it is juxtaposed with two things, right, and this is the electrical excitation part. And I am trying to suppress the mechanical excitation with the application of the electrical excitation. Now, when A tilde s, let us say the very special case when the admittance is constant, then let us denote omega 1 square as k 1 by omega 1 and omega p square as k p by m p, and applied voltage V bar is k x 1, it is proportional. Suppose I put a control law. So, this is what is my control law, that my control law is that to apply a voltage which is proportional to the amplitude of the displacement here. So, if I do that, then I am going to get a relationship where the V bar is gone now, and you have a relationship between x1 y and you have this the voltage which is proportional to x1 itself. Now, let us further in this particular relationship, of course, where is the control part? You have to keep that in your mind. Okay, so, alpha bar here is having A bar k A over k, which means that is having the control part, because you have the control law there which is embedded inside this system. We also have another parameter beta bar, which is Cp plus A tilde k A k b over m p. Now, since you have already chosen Cp k A k b m p and you have considered the A tilde s to be constant, so you are not going to get any change here, but this alpha bar you can actually tune. So, now you can rewrite the relationship as if you take both x1 terms in one side, then it will become 1 plus alpha bar s square over s square plus beta bar s plus omega p square times x1, and that equals to omega 1 square over s square plus omega 1 square y. So, that is the very special case kind of a thing, where the relationship between x1 and y is of this nature. Now, in this particular case, you have to see that in the absence of this alpha bar part, so suppose the gain k is 0, so then this alpha bar part would not have been there. So, then what would have happened? Your x1 then would have been simply omega, in the case when alpha bar is 0, omega 1 square over s square plus omega 1 square y. Now, that is the classical case of an undamped system. In fact, this system has two roots, right. So, if I find out the two roots S1 and S2, then this system will be having your roots as square root of S1 S2 as square root of omega 1 square, which will give you two solutions, that is you will be having S1 as either omega 1 or you can actually plot them in the minus omega 1 also has another solution. So, you can plot them in the imaginary axis itself, both plus and minus as the two solutions of it. So, because they are imaginary, so you are getting plus minus. So, you can say that plus minus j omega 1, both of them will give you the solution, because it is s square equals to minus omega 1 square, right. So, you are going to get a plus minus j omega 1, and as a result in the root locus, if you plot it, that means the root locus of real over s and imaginary of the root s, then this is going to give me 2 of the poles here. This numerator is going to give us the 2 poles, and both the poles are on the imaginary axis, and that is the telltale sign of an undamped system. So, that is what it would have been if my alpha bar would not have been there. If I introduce the alpha bar, what may happen to the system? So, in that case we can actually write this whole equation together, and we are going to see that we have a denominator in which we have a numerator in which we have 2 zeros, and we have a denominator in which we have 2 poles here which are undamped, and we have 2 poles here, and we have 2 zeros here. So, essentially this will be a case of, if I just try to plot it here, once again because of the introduction of this alpha bar term, then we are going to see that we have 2 undamped poles here, and along with that we have 2 additional poles there, and these 2 additional poles you can place anywhere depending on wherever you wish to do it. So, essentially you can place these poles on the real axis or somewhere as complex conjugate, you can put it, and you have 2 zeros in the system. So, these 2 zeros are once again complex conjugate, and you can put them anywhere in the system. So, if they are in the left half plane, then of course it is fine, but if they go to the right half plane, then you will have problem. So, we will see that in certain cases it can happen, so that they can go to the right half plane, and in other cases when they are in the left half plane, they may get attracted towards these poles may get attracted towards these zeros, and these poles may actually diverge. So, you can get various solutions with respect to the change of the gains, and we can see one typical solution corresponding to a unit gain system, where you can see here that you have these are the 2 poles here, as you can see, and also as the third pair is somewhere here which is also very close to 0, and corresponding to a positive gain, you can see that a part of it can actually go to the right half plane. So, a proof mass actuator, if it is not controlled properly, then it is possible that it can add actually energy to the system, and it can generate instability. Otherwise, if this does not happen, then it can happen that it will follow approximately this course, and provided I put a proper pole 0 placement, and which I will talk about it when I will talk about root locus, and you get these 2 systems as the 2 damped systems with whatever damping that you want to apply to the system. So, this is the damping ratio. So, by designing the alpha, you can make the system very stable as well as very well damped. Suppose these are the positions of the closed loop poles, that could be some of your goals, and the 2 undamped modes just do not, we can make sure that it do not come to the right half plane to create an instability. So, these various possibilities will come up with the proof mass actuator, and that is what is a good control design problem, and we will talk about such a problem in our discussions on active control. So, this is where we are going to finish today, and we will also talk about in the next lecture on different springs for isolations and viscoelastic dampers. Thank you.